Okay, we're back here for this week's second video of the lecture series. I'll get into stuff here. So this is part one. We're going to continue on with what we talked about in the last video, which was confidence intervals. We'll get into a little bit more about confidence intervals and how to use them. Then we'll get into what's going to be a large part of the lecture series, which is going to be hypothesis testing, how we can set up a formal statistical hypothesis test to determine whether we're going to reject or not reject a null hypothesis, what a null hypothesis is, what an alternative hypothesis is, things like that. So let's get back a little bit more into confidence intervals. So again, just to reiterate why we use confidence intervals, right? We're trying to approximate how much error we have in our sample mean, our X bar, and how well it does at predicting what's going to be our population mean. Put my highlighter up here, laser pointer. Right, so we're trying to use our sample mean X bar to predict our sample mean or population mean, and we're going to use confidence intervals to be how sure of whether that population mean mu is going to fall within that confidence interval, right? Because remember, we want to predict the population mean, but usually we don't even know what that population mean value is going to be, right? And of course, we can't go out there and sample everything or measure everything, so we have to make an estimate using a sample. So confidence intervals, the way they work is that we put a range, right? Interval range around our sample mean, and then we can assign a certain confidence, hence the term confidence level or confidence interval, that the population mean mu will fall within that range of values, right? So this is why these confidence intervals work, right? So the idea is that if we go and take a whole bunch of sample means, we can assume, and the assumption here is that those sample means, we plot them up, will start to form a normal distribution. So they'll be normally distributed, these sample means X bar, around the population mean. So this is essentially, again, that central limit theorem in practice. So what do I mean here? Well, imagine, right, here's my population mean, which I basically am trying to predict using my samples. And the central limit theorem says if I take a whole bunch of samples, right, their means X bars, they will form, right, they'll start to approximate a normal distribution with more, of course, of the values being centered around the population mean, and more of the extreme values for the samples being further and further away, hence being less probable than the values towards the middle of the distribution. Right, so we can define the confidence intervals and how they work. So imagine I take 7 samples. There's my means of my 7 samples, right? And again, they're trying to predict what the population mean value is going to be, right? I can, right, start to put some intervals or a range around each of these X bars, right? So we can see there, if I set my confidence intervals as to plus or minus 1 standard error. We talked about the standard error last time and how to calculate it. So each of these intervals is defined as being plus or minus 1 standard error above each of these sample means. So I can see now, right, within each of these intervals, most of these confidence intervals capture the population mean mu, right? All except here. This one down here doesn't, and this one here also doesn't. But each of the other confidence intervals, right, has the population mean actually falling within them. So in this case, if we use 1 standard error, we can be about 68% probable or confident that the population mean will fall within that confidence interval. But usually we want to be a little more confident than just 68%. So we could assign and put our confidence interval equal to plus or minus 2 standard errors above and below each of these sample means. So now with the green arrows, right, this is my 2 standard errors above and below each sample mean. Now we can be 95% sure that the population mean is going to fall within each of these intervals, these confidence intervals. So now we can see that all except for this sample down here, the population mean value falls within each of these confidence intervals for each of the other 6 samples. Then if we want to be even more sure, we can extend our confidence interval so they're equal to 3 standard errors above and below the sample mean. So now I can see, right, because it's a normal distribution, 3 standard errors above and below the mean is going to capture about 99% of the area underneath the curve. So now you can see that all of my 7 samples, right, and the confidence intervals that are drawn around them capture the population mean value. So this is the idea behind how we use confidence intervals. So going back to the end part of the last video when we were talking about sampling and our pesticide bee example, right? So we're interested in going out and measuring the effect of pesticide use on bee populations, right? That's our target population is across Canada. So say I go out and I do my measurements at those bee farms in Quebec, 50 bee farms with pesticide use and 50 bee farms without pesticide use, and say that from my results, 27% of the bee farms exposed to pesticide experienced die-offs. Okay, so but how sure can I be that this sample mean, my X bar, is representative of the effect of pesticides across the country? So this is an example of using, right, the sample mean and trying to extrapolate to the larger population or target population. So sometimes you'll often see the results from a sample stated in this way. So for our bee example, right, say our conclusion from our study is, according to recent research, which is our study, 27% of the bee farms exposed to pesticides experienced bee die-offs. Now this 27% is our sample from the 100 bee farms in Quebec. And then you have this statement. This estimate is considered accurate within 6 percentage points, 19 times out of 20. But what does that statement actually mean? Well, we can break it down, right? So 27% is our sample estimate. In this case, probably it's going to be like the mean or the median or something like that. That's our X bar. So that's a result. Now that's 6%, right? 6 percentage points plus or minus above and below that 27. That's our confidence interval. That's the range that we're going to put around our 27%, in which we can be, in this case, 95% sure that the overall population mean, the bee population throughout entire Canada, is going to fall within that confidence interval, that plus or minus 6% points above and below 27%. So that's called the confidence level, how sure we are that that value, population value, is going to fall within that confidence interval. So here's just another example, right? So imagine there's another study done, go out and there's a sample taken to a recent poll. The average driving time for commuters in, say, Tokyo is 56 minutes, accurate to within plus or minus 4 minutes, 90% of the time. Now, this is a common way that often the results of a study or a sample are expressed. So when you see something like that, you know that our sample estimate, our X bar, is 56 minutes. Now it's accurate within plus or minus 4 minutes. So that's our confidence interval. So we're going to minus 4 minutes and add 4 minutes onto that sample mean, our X bar. In this case, we're 90% sure. That's our confidence level. We're 90% sure that the population mean is going to fall within that confidence interval of plus or minus 4 minutes above and below that sample mean. All right, let's do our own example here. So imagine you went out and you're interested in measuring rocks. So you go out to Vancouver Island on Sombrio Beach, right, and you measure 100 rocks or pebbles for their diameter, right? And so you get an average diameter from your sample of 100 rocks of 8.5 centimeters and a standard deviation of your sample of 1.5 centimeters. So how could you determine a confidence interval for this sample? Well, the size of your confidence interval is going to be dependent on a few things, right? So the first thing is like how much variation is going to be in your sample of 100 pebbles. Is there a large variation in size, or are they all about the same size? So as the variation increases, that's also going to increase our standard error, right? So that's going to require then a wider confidence interval. So how much variation is in our sample? Also the size of the sample, right? In our case, it's 100 measurements. But as our sample size increases, we can be more sure in our confidence interval, and we can actually narrow our confidence interval. And the third thing is, well, how confident do we want to be? Do we want to only be 90% confident that the population mean rock size is going to fall within our confidence interval, or do we want to be very, very sure, i.e. 99%? So those three things are going to determine what our actual confidence interval is going to be. So back to our data here, right? Our X bar, our mean from our sample is 8.5 centimeters for our diameter. The sample standard deviation is 1.5 centimeters, and our sample size is 100 rocks. So we can use that data to calculate our standard error, which we're going to use to construct our confidence intervals. So that gives us a standard error of 0.15. So if we want to construct a confidence interval of 68%, right? How we do that is basically we're going to add our standard error of 0.15 centimeters onto that 68%, or onto, sorry, our mean diameter to get our confidence interval. So if we're just wanting a confidence interval of 68%, right, not a very high confidence interval, usually not used, how we're going to determine that confidence interval is that we're going to take our sample mean, our X bar, add and subtract our standard error onto it. So that's also the same thing as this here, taking our sample mean and then adding and subtracting our standard error. So for this example, right, our sample mean is 8.5 centimeters. Our standard error we calculated is 0.15 centimeters. So we're going to add and subtract that 0.15 centimeters to our mean. That gives us a low value of our interval of 8.35 centimeters and a high value of 8.65. That's really only, right, that's only 68% confidence interval, because we're only adding and subtracting one standard error. Remember, the standard error kind of works like standard deviations, right? Most of the probability or the area underneath the curve is between plus and minus one standard error or one standard deviation above and below the mean. So in our case, right, we have a confidence interval for 68% confidence level, low value basically going from 8.35 centimeters up to 8.65 centimeters. But 68% is not very sure, not very confident. So what if we wanted to be a little more sure and determine the 90% confidence interval, which is more typical of the confidence intervals that you usually calculate? Well, basically the way you're going to do that is just kind of modify what we did to calculate the confidence interval for the 68% confidence interval. But now we're going to add in the Z-score for the 90% confidence interval. Remember, you guys know now how to calculate Z-scores, right? You take your raw data value minus the mean divided by the standard deviation. So to determine the 90% confidence interval, same kind of idea. We're going to take our sample mean, but now we're going to add and subtract the standard error multiplied by the Z value for 90%. So multiplying the Z value by the standard error, that's the same as multiplying Z by the sample standard deviation divided by the square root of the sample size. So what's this going to look like is that we're going to have our sample mean of 8.5 centimeters. Our Z value for 90% confidence interval is 1.65. We multiply that by the 1.5 centimeters, and we get a confidence interval for 90% equal to 8.5 centimeters plus or minus 0.248 centimeters. So if we add and subtract that value, now our 90% confidence interval is going from 8.25 centimeters up to 8.75 centimeters. So you might be wondering, why multiply that Z value of 1.65 for a 90% confidence interval? Where do you get that 1.65 value from? Well, if you think back to the Z tables that we looked at a couple lectures ago, right? The Z value of 1.65 corresponds to, in this Z table, 0.4505. So if you round that to 0.45, right, on both sides of the average value, if you add 0.45 to 0.45, that gives us 0.9. In other words, 90% probability corresponds to a Z value of 1.6. Add on to 0.05, that gives you 1.65, Z value of 1.65 for a 90% confidence interval. So that's where that Z value comes from. So you can think about it like this. Here's our normal distribution, 90% of the probability or the area in the middle here, right? 5% on each of these tails give us the other 10%. Here are Z values, right, corresponding to a negative 1.65 and a positive 1.65. So each side of the mean there, right, I have 45% of the area underneath the curve going out to minus 1.65 and plus 1.65. So add those two together. That's where I get the 90% and the 1.65 Z values. So now for our pebble or our rock example, right, my 90% confidence interval, of course, is much larger than my 68% confidence interval, right? Because as my confidence interval expands, I can be more confident that the population mean is actually going to fall within there. So 8.5 being my sample mean, there's my low value, Z value, minus 1.65 for the 90% confidence interval, and plus 1.65. So those correspond to, in this case, as we saw in the calculation, the low value of 8.25 up to 8.75. That gives me my 90% confidence interval. So here's just going through the calculation in the Excel spreadsheet, which I'll put in Moodle. So I set it up here. There's my sample mean, 8.5, my sample standard deviation of 1.5, my sample size is equal to 100. And then down below, you can see where I have calculated my standard error. Click on that. You can see there's the equation, which is going to be, right, the standard deviation divided by the square root of the sample size. So there's my Z score for 90%, 1.65. I'm going to multiply my standard error by that Z score. And then I'm going to both add and subtract that value from my sample mean to give me my confidence interval. So there, for a low value of 8.25, for a high value, I have 8.75. You can see I've also done it for the 95% confidence interval, which we'll look at in a little bit here. So the Z score, of course, is higher for the higher confidence interval. And then for the 99% confidence interval, you can see that the Z score is even higher. So I get a larger confidence interval. So just a couple of screenshots, right? There's my standard error, which I've calculated. And there's my corresponding confidence interval for 90% confidence interval. So you can see, right, for the 95% confidence interval, the interval gets wider. So I can be more confident that my population mean is going to fall within there. And then if I want to be 99% sure that my sample confidence interval is going to capture the population mean, right, I can calculate the 99% confidence interval, which is even wider, as expected. So usually the most commonly used confidence levels, right, are 90%, 95%, and 99%. So here they are in a table right here. So there's my confidence level or probability, right? And then the opposite or the complement of that is our significance level, okay? And then there's our associated Z score. So we already saw for a 90% confidence level, we have a Z score that corresponds to a Z score of 1.65. For a confidence level or probability of 95%, it's a higher Z score, and then even a higher Z score for a 99% confidence level. So what do these terms mean? Well, on the left here, our confidence level basically is telling us the chances that we're right. In this case, the chances that the population mean is going to fall within that confidence interval, right? As you increase your confidence level, you can be more and more sure that that interval is actually going to have the population mean fall within it somewhere. The significance level, right, is basically, right, the opposite of the confidence level, and it's the chances of being wrong. So as our confidence level increases, our significance level decreases, right? So as our confidence that we're right increases, our confidence that we're being wrong or that we will be wrong decreases, right? So as one goes up, the other goes down. So you can think of significance as the chances that your test is going to give you the wrong answer. But we'll come back to this idea of confidence and significance a little bit later in this video when we start to look at hypothesis testing. So let's look at the 95% confidence interval. So for the 95% confidence interval, as I just showed, that's going to correspond not quite to 2 standard deviations or standard errors above and below the mean, but it's close, right? It's 1.96. So you can see that 95% of the area underneath the normal distribution extends out to minus 1.96 on the left-hand side and plus 1.96 standard deviations or standard errors above the mean on the right-hand side. So say if we wanted to calculate the 95% confidence interval, how would you do that for our pebble rock example? Well, again, we're going to take our initial calculation for the 68% confidence interval, and now we're going to add the z-score for the 95% confidence interval, which in this case is going to be 1.96. So in this case, we're going to take our sample mean, and we're going to multiply our sample standard deviation by the 95% z-score, right, divided by the square root of our sample size. So of course, now for 95% confidence interval, right, we're going to have a wider confidence interval. Now we have a confidence interval of 8.21 up to 8.79. So we go back to our diagram here, right? Now, as our interval gets wider, we can be more and more sure that our population mean mu will fall somewhere in between those two values. Right? So now we're up to the 95% level of being right. And in this case, being right is that our population mean will fall within that confidence interval somewhere. So basically the idea here is as we start to expand our confidence interval and make it wider, we can have a higher level of confidence that our population mean will fall somewhere in there, right? It makes sense if we have a very narrow interval, right? There's less of a chance, or less of a chance that our population mean will fall within it, and more of a chance that we'll miss it, and the population mean will fall somewhere outside of it. So there's this trade-off between the confidence interval and the confidence level, okay? So as we start to increase our confidence interval or make it wider, right, we can be more certain that our population mean is going to be in there, but then again, our confidence interval or our range is also wider. So we cannot be as precise as maybe we want to be. So say, extend for our example here, say you wanted to calculate the 99% confidence interval and compare the results for the 99% to the 95% confidence interval. Use the same data as before, right? For our pebble examples, so the steps that you'd follow, like look up the z-score for the 99% confidence interval, multiply the standard error by that corresponding z-score, and then subtract and add that value to your sample mean. So here's just another example, different example from the rock example, right? So in this scenario, imagine you have a sample of 25 local schools that show on average classes have 28 students and a standard deviation of 7 students. So using that data there, determine the 90%, 95%, and 99% confidence intervals for that sample estimate. In this case, the sample estimate is going to be 28 students on average, standard deviation of 7 students. So you're going to follow the same procedure as we just went through with the rock example, just for a different scenario. So you can look at this in the Excel spreadsheet. So this is class calculation number 2, confidence interval. So there you input your data, right? Your sample mean, sample standard deviation, sample size, and then you can, from that, you're going to calculate your standard error, determine your corresponding z-score for the 90% confidence interval, multiply it by the standard error, and add and subtract that to your sample mean. So I'll let you guys try that one for yourselves. So just to summarize, right, with our confidence interval, basically, right, with our sample mean, right, that is something that we know that we've measured, but usually what we're after is the population mean. Standard deviation of the population, usually we do not know that either, just like the population mean. And then we're also going to be using the standard error of the mean calculated by the standard deviation of the sample and the sample size. Okay, so we've been talking so far about using z-scores to determine our confidence intervals, right? But that's usually only permittable or applicable or appropriate, I should say, when we have relatively high sample sizes. Because what happens when we start to encounter very small sample sizes, like we're talking about, less than 30 or 25 for an n, confidence interval is usually underestimated. It's going to be too narrow when we're dealing with very small sample sizes. So we can't use the z-score to determine our confidence intervals. We have to use a different distribution. So instead of a normal distribution or a z-distribution, when we're dealing with very small sample sizes, we're going to instead rely on what's known as a t-distribution. And this actually, there we have a comparison of our z-distribution in purple here, right? That's our regular normal distribution, right? The t-distribution with a smaller sample size, we tend to have a more platykurtic, more flat distribution. And therefore, using a z-score to determine our confidence interval is not appropriate. So we have to use this t-distribution instead. Right, so just a graphic illustrating the differences between a normal z-distribution, where we have a relatively high sample size, usually 30 or more. When you start getting down to sample sizes of about 30 or less, right, you can see how the distribution gets more platykurtic, more flat, and therefore we cannot reliably use the z-distribution anymore, and we have to rely upon the t-distribution. So that brings us to inferential statistical tests, which we're going to be looking at in this week's lab, looking at these t-distributions and z-distributions to do various calculations. So just go over a little bit what we'll talk about in the last part of this video. We're going to get into now what's referred to as classical hypothesis testing. How do we formulate and set up a classical hypothesis test, and how do we carry out the calculation and determine our hypothesis testing? So we're going to look at the 6 steps for completing a classical hypothesis test, and we're going to be using 2 distributions to calculate what's known as our test statistic. So we're going to be using a z-score for very large sample sizes, and the first test that we're going to be using is what's referred to as a one-sample difference of means test. Okay. But if we have a large sample size, we can do a one-sample difference of means test using a z-score. If we have a relatively small sample size, we're going to do the one-sample difference of means test using the t-score or the t-distribution. That's the fundamental difference right there, depending on the sample size. So here's the 6 steps that we're going to be using to carry out a classical hypothesis testing. First one is going to be formulating our null and alternative hypotheses. So we're going to go over what our null and alternative hypotheses are. Once we've done that, we're going to select what's the appropriate stat test that we're actually going to use. We're going to select our level of significance. Remember, level of significance is the probability that our test will give us the wrong answer. Then we'll use that to determine the areas underneath the curve where we're going to either reject or not reject the null hypothesis. Finally, we'll calculate the actual test stat, whether it be a z-stat or a t-stat. And then based on that test stat, we'll make a decision whether we're going to either not discard or not reject the null hypothesis, or we're going to go with the alternative hypothesis. So we'll be going over these 6 steps, lots in the next few lectures here. So first things first, let's determine how we can set up a research question. So imagine, right, we're interested, we've been observing golfers putting, and you're wondering, well, do golfers do better or worse if they're putting in front of an audience, in front of a crowd, or if they're putting alone? So this could be your research question, right? Do people perform differently, say in putting, when they're being watched, or compared to if they're alone? So once we got a research question in our head, we can turn that into a research statement, something that we're going to use to test. So our research statement from this question might be something like, will people produce more errors on a difficult test when somebody is watching them compared to when they are alone? So that's what we're trying to find out from our research question. So in our example, there are really only 2 possible outcomes, either one or the other. Our null hypothesis in this case is going to be that people perform at the same level when they're alone and compared to when they have people present. So it really, the null hypothesis is that there's no difference in people's performance in putting when they're in front of a big crowd compared to when they're alone. There's no difference. That's our null hypothesis. Our alternative hypothesis is that there is a difference, right? That people perform differently when they're in front of a crowd, right, compared to when they're just performing the same task alone. So there's our null hypothesis and our alternative hypothesis. Now, basically, we're going to be using our stat test to determine which one of these we're going to choose. We have to choose one. We can't not choose both. We either have to go with the null hypothesis, fail to reject it, or if we reject the null hypothesis, we're going to go with the alternative hypothesis. So in more general terms, what is the null hypothesis versus the alternate hypothesis? Well, our null hypothesis you can kind of think of as our default, right? It's basically what we're assuming is happening, right? And when we reject that assumption, we're going to go with what's going to be our alternative hypothesis. Again, these are mutually exclusive. So you either have to, at the end of your test, either pick your null hypothesis, or if you reject it, go with the alternative hypothesis. Right, so just a couple more examples, right? So you can think of some research questions, right? Is there a difference between the number of NHL hockey players from Quebec versus British Columbia, right? So what would be your research statement? What would be your research question there? So you can also think of the null hypothesis as the default assumption that there's no significant difference or relationship between 2 variables. And what you're seeing is actually, any difference that you actually do see is just due to sampling error, random chance. So with our null hypothesis, right, usually symbolize H0, right? Our null hypothesis usually is going to be that there's no relationship or difference between variables in the population. In terms of correlation, right, how well associated 2 variables are, the null assumes that there's no correlation between 2 variables. So the correlation in this case is symbolized by this kind of funny row P here. So in terms of correlation, right, this is what we're doing with our scatter plots, right? Our null hypothesis is that there would be no correlation, no relationship between variable X and variable Y. It's only when we reject that null hypothesis that we can go with either, say, if there's a relationship, whether it be negative or whether it be positive. So, right, another example of a null hypothesis that there's no difference in, say, the performance or the mean value between 2 population groups, right? A lot of studies look at differences in some variable between men and women. So the null hypothesis in that case would be that there's no difference statistically between what the value is, say, for a mean value between men and a mean value for women. So if you took the mean value for women, subtract it from men, you'd get 0, aka the mean for men is essentially the same as the mean for women. So if the differences that we actually do see, right, and we're trying to determine whether they're statistically significant or not, with the null hypothesis is assuming that the differences that we actually do see, say between two groups, or in this case 3 groups, is not significant and is only the result of a random sampling error from the overall population. So here at the bottom here, here's our overall population. Imagine you took 3 samples out of it. You can see that those 3 samples are different, but are they statistically different? We can see that there are differences, but the null hypothesis would be that the differences that are apparent, that we do see, right, are just from random chance and are not significant. So if we reject the null hypothesis, we have to go with the alternative hypothesis, sometimes symbolized by H subscript A or H1. So when we go with the alternative hypothesis, that indicates that there is some significant relationship between 2 variables, that there is a correlation that is not random. So in this case, we reject the null hypothesis. In terms of correlation, we're going to go with the alternative hypothesis that there's either significant positive correlation or significant negative correlation, that there is a relationship between our 2 variables. And like I said before, for the alternative hypothesis, we would, right, determine that there is a significant difference in some value between 2 groups, say between men and women. So let's look at an example here. Imagine that you are interested in determining whether Victoria has a different number of sunny days than Montreal. Right? So you look up the number of days that are sunny in Victoria, the number of days that are sunny in Montreal. You see that there is a difference, but you're wondering if this is statistically significant or not. Right? So how we formulate our null hypothesis and our alternative hypothesis. So in this case, right, the null hypothesis, right, is the assumption that we're beginning with, and it's the opposite of what we're testing. So in our case, we're trying to see whether there's a difference in sunny days between Victoria and Montreal. So if we go with the opposite of what we're testing, our null hypothesis for this example is that there's no statistically significant difference in the number of sunny days between Montreal and Victoria, right? There are differences, but those differences are just due to random sampling errors. So if we reject the null hypothesis, we're saying basically that there is a statistically significant difference in the number of sunny days in a year between Montreal and Victoria. So again, you either have to go with one or the other. If we reject the null hypothesis, we're going to go with the alternative hypothesis. And so this brings us to the topic of directionality and tails. So this basically tells us how we're going to set up our null hypothesis and our alternative hypothesis. So we're going to talk about two-tailed tests, which are also referred to as non-directional tests, and one-tailed tests, which are aka directional tests. So what do I mean by two-tailed and one-tailed test? Well, a one-tailed test, right, is basically a test where you're trying to figure out whether one variable is greater or less than another variable, right? So down here, here's a one-tailed test. So you can see that we've isolated this area down here compared to the rest of the distribution. So that's a one-tailed or a directional test. A two-tailed or non-directional test doesn't care whether one variable is greater or less than another, right? Which one is greater and which one's less. It only cares whether there's a significant difference between the two variables. So it doesn't care whether which one is greater than the other one. It only cares whether there is a significant difference between the two variables. So that's what's referred to as a two-tailed or non-directional test. So here's an illustration of, right, one-tailed hypothesis, right? So you can see here we have what's known as our rejection area, right? We'll get into this in a little bit here. Our rejection area 5% of the area on the right side there, or we could also put it on the left side there. We could also split that area, that 5% rejection area, in half and put it on both tails, being a two-tailed test. So you can see that the area in the non-rejection area of the curve is still 95% for all of these examples, but it's just the position that we put the rejection area in compared to the non-rejection area. So here's a table giving us, right, our confidence level going from 90%, 0.9 up to 99%, and our alpha level for our one-tailed test. We'll get into it, what these mean in a little bit going through our examples here, our critical value. And then, so in the yellow here is for our one-tailed test, right, directional test. And then in the green here are our alpha levels and our critical values if we do instead a two-tailed or non-directional test. So imagine we're starting out with a 90% confidence level. If we're doing a two-tailed test, right, we know that our Z values are going to correspond to plus and minus 1.65. Right, so there's our Z values right there. So the white is going to be our non-rejection area, right? We're going to stay with the null hypothesis. But if we get further away to the outside within the red zones here, that's going to be where we reject the null hypothesis and go with the alternative hypothesis. So you can see here with two-tailed test, we've split the rejection areas in half and put half of it on the right side and half of it on the left side. Alternatively, right, if we went with a one-tailed test, we would take that 10% rejection area, right, and put it either all on the left side, right, or alternatively, we could put it all on the right side. So now that you can see that it's also changed what's known as the critical value, which we'll talk about and show you in examples here. So our critical value has changed now to the left side test minus 1.28, which divides the rejection and the non-rejection areas. And if we do a right-tailed test, our critical value is the plus 1.28. So anything above that is the rejection, sorry. Anything below that is the non-rejection area. So you can see that for the same confidence level, right, whether we do a one-tailed test or a two-tailed test, it's going to change where our critical values lie. So imagine it's a little confusing so far, but we're going to go through lots of examples here to hopefully better explain it. So if we move instead from a 90% confidence level up to a 95% confidence level, same kind of idea. So we do a one-tailed directional test. Our critical value, if we on the left side, minus 1.65. Directional test, right? For our rejection area on the right side, going to have a critical value of plus 1.65. And if we did for a 95% confidence level, our two-tailed test, we would split the rejection areas, right, in two and put them on each side. So now instead of having 5% rejection area for the directional test, we split it in half, so we have 0.025 on each of the tails. And you can see that the critical values are further out for the two-tailed non-directional test compared to the one-tailed directional test. So you can think about it like this, right? So for a left-tailed test, what we're basically trying to figure out whether our population mean is going to fall to the lower end, below, in the rejection zone. If it's above that area, we're going to be in the fail to reject the null hypothesis area. The other direction, right, if we put it on the right-hand side, it's going to say that our population mean mu is much larger and falling within the rejection zone on the right side of the one directional test there. And then for our two-tailed test, non-directional, right, we only care about whether the population mean is going to be any different. It doesn't matter whether it's greater or less than the sample mean. We're just wondering if it's differently significant or not. Right, so for our example, right, our null hypothesis is going to be that there's no statistically significant difference in the average number of sunny days between Victoria and Montreal. For our alternative hypothesis, depending on whether we're going to do a directional or non-directional test, we could have up to 3 different alternative hypotheses. If we go with the two-tailed test, we'd only be looking at if there's a statistically significant difference in sunny days between Montreal and Victoria. Let's say we were interested maybe in doing a one-tailed test. So one version of the one-tailed test would be if we're trying to figure out if there's significantly more sunny days in Victoria than Montreal, or we could flip that around and do the one-tailed test that there instead it's going to be fewer sunny days in Victoria compared to Montreal. So going back to our diagram here, right? So there's going to be our two-tailed test where we're only interested in if there's a difference in sunny days between Montreal and Victoria. In the middle there are our right-tailed tests, right? That would be what if our research question was if there's significantly more sunny days in Victoria than Montreal. And then our left side directional test would be if there are significantly fewer sunny days in Victoria compared to Montreal. Okay, so this brings us to statistical tests for difference. So a main use of statistical tests is to determine whether there's a significant difference between two samples or two groups or not. So the first type of test we're going to be looking at is called the one sample means test. And what the one sample means test basically is, what it does is it takes a sample, looks at the sample, and the test tells us whether it belongs to a larger population or not. So when we're dealing with small sample sizes, we're going to be doing t-tests. So we're going to be doing 3 types of t-tests in this class. The first one is going to be the one sample t-test. Then we're going to move on to independent samples t-test, and then the paired samples t-test. So let's get back to the one sample means t-test. So again, we can either use a normal distribution or a t-distribution if we have a really small sample to determine whether our sample belongs to a larger population or not. Right, so basically we're using the one sample means test to determine whether our sample mean belongs to a larger population or whether that sample is significantly different from the overall population. So that's hence where the term one sample means test comes from. We're comparing the sample mean to the population mean and determining whether the sample mean belongs to that overall population or not. So the idea here behind the one sample means test is that as you get further as the sample, say your X bar, gets further and further away or more extreme value away from your population mean, it becomes less and less likely that that X bar or your sample actually belongs to that population. So imagine you have a X bar value, which is relatively close to your population mean, right? It's more probable that both that sample belongs to that larger population. But as your sample, right, say if you get a really low value for your sample mean or alternatively a very large value for your sample mean compared to your population mean, it becomes less and less probable that that sample actually belongs to that same population and becomes more likely that that sample is coming from a completely different population. So this is essentially what the one sample means test is determining. So in terms of interpreting the hypothesis, right? So we reject the null hypothesis if your test tells you that there's a significant difference between the sample and the population in a one sample means test. So how can we evaluate and determine whether we're going to retain or reject the null hypothesis? Well, there's basically 2 ways. One is calculating the test stat, whether that be a z-score or a t-score, and compare our calculation to a critical value. And whether that test stat is above or below that critical value will determine whether we're going to either fail to reject the null hypothesis or decide to reject the null hypothesis. Another thing we can use, and we looked at in the lab already, is looking at the p-value, right? And comparing that p-value to what's known as a significance level, sometimes also called the alpha value, which I'll mostly be referring to the significance level as the alpha value. So two comparisons we can use to determine whether we're going to fail to reject the null hypothesis, or we're going to reject the null hypothesis and go with the alternative hypothesis. So the general idea here is, if we have a sample mean x bar that falls within this range, right, we're going to fail to reject the null hypothesis. Instead, if our sample means fall within the rejection zones, which are more extreme, further away from the middle than the critical value, either on the negative or the positive side, that's when we would reject the null hypothesis and go with the alternative hypothesis. Right, so the p-value, so what does p-value actually tell us? Well, it's one way to quantify the probability that the sample belongs to a larger population for that sample. So you can think of the p-value as a probability of getting that sample mean, that x bar, or some other more extreme value, under the assumption that that sample actually does belong to the population. So as your p-value gets smaller and smaller, it becomes less and less likely that that x bar, that sample mean, actually belongs to the same population as your population, or as your population. Right, so looking at it in terms of a diagram, so the idea here is, as your p-value, right, you have more area underneath the curve and your p-value gets smaller and smaller, that indicates that there's a much less or lower probability that your sample mean is actually coming from the same group as your overall population. So again, the idea here, so imagine I have a sample mean x bar 1 right there. You can see that's relatively close to the population mean, which in this case we know. So in this case, right, to the left of my population mean, I have 0.3 of the area underneath the curve, indicating that I have a p-value of around 0.3. So there's a 30% chance, right, that that sample mean actually belongs to the same group as my population. But imagine I have another sample mean, x bar 2. You can see that it's more extreme, further away from the population. In this case, the area underneath the curve above that value has a much lower p-value. So 0.04, or about a 4% chance that x2 actually belongs to the same population as mu. So that's how you can interpret the p-value. Right? So again, as your sample value, or sample mean, which is usually what we're determining in this case, gets further and further, more extreme, either higher or lower away from the mean or the population mean, it becomes less and less likely that that sample actually comes from that larger population, and that it comes from a completely different group. That's essentially what the one sample means test is telling us. So how we determine whether, and how we can use the p-value to determine whether we're going to accept is not a really good term, or fail to reject the null hypothesis or reject the null hypothesis, is that we set what's known as a significance level, aka an alpha level. That at the alpha level is basically the threshold whether we're going to use to determine whether we're going to reject or fail to reject the null hypothesis. So really, in the end, there are only two conclusions that you can make by the outcome of your statistical test. You can either, right, reject the null hypothesis, or you retain or fail to reject the null hypothesis. So you have to do either one of these. You can't do both. You can't do none of them. You either reject the null hypothesis and go with the alternative hypothesis, or you retain, aka fail to reject the null hypothesis. So I know in a couple of the slides before, it said accept the null hypothesis, but really you never really accept the null hypothesis. You only fail to reject the null hypothesis. There's not enough evidence from your statistical test for you to warrant rejecting the null hypothesis. Let's talk a little bit about error. right? Because our statistical test isn't foolproof, right? It can actually give us the wrong conclusion, and that's what is really all about selecting the appropriate confidence and significance levels, right? There's always a chance that the conclusion from your test is going to be wrong, okay? So kind of a rule of thumb here is that the null, hence the term null, right? It's kind of like the default, is presumed correct until it's shown otherwise. So you can actually retain the null, stick with the null hypothesis, even though it's not true. In that case, you should have rejected it. But there's always a chance that we wrongfully either retain the null hypothesis or we, in error, reject the null hypothesis. And this results in two different types of errors associated with these hypothesis testing. So the first type of error, known as a type 1 error, is when we have a true null hypothesis, but we reject it, right? So the null hypothesis is actually the correct answer, the real answer, but our test tells us to reject it when we shouldn't. So that's sometimes referred to as a false positive. The opposite of that is a type 2 error, where the null is false, but we fail to properly reject it. So this is called a false negative. We should reject the null hypothesis, but we fail to do so. So a pretty good illustration of the difference between a type 1 and type 2 error, right? False positive, right? The doctor telling this guy, right, you're pregnant, right? So that would be falsely rejecting the null hypothesis that he is not pregnant. And then the opposite is a type 2 error, false negative, where this woman is pregnant, but the doctor says, no, you're not pregnant. So she retains, in this case, the doctor, the null hypothesis in error. So with our type 1 error, false positive, right, we have a true null hypothesis, but we reject it anyways in error. And how we determine the probability that we're going to commit a type 1 error or a false positive by our hypothesis testing is by that alpha level, or our significance value or level. In terms of our type 2 or false negative error, right, that's when we fail to reject the false null hypothesis. And the probability of committing a type 2 error is set by not the alpha value, but the beta value. We're going to be talking mostly about alpha values and significance levels, but just keep in mind that the beta value is the probability that we would commit a false negative outcome for our stat test. So keep in mind that we generally assume that it's more serious to commit a type 1 error, a false positive error, compared to a type 2 error. But it depends on the question that you're asking and how the test is set up. So to look at it in graphic form, right, so you can imagine here, our alpha value, you can again think of it as the threshold or the line which divides the area underneath the curve where we're not going to reject the null hypothesis, and to the area underneath the curve where we're going to reject the null hypothesis. Right? So we can think of that alpha value as that threshold dividing the rejection zone from the non-rejection zone. So the alpha value, more generally referred to as the significance level. So basically that alpha tells us the probability that our test is going to commit a type 1 false positive error. So the smaller and smaller our alpha value gets, right, the lower and lower chance there is that our statistical test will cause us to commit a type 1 false positive error. Right, so basically what we're doing, right, is that from our statistical test, we're going to get a p-value, right? We've calculated p-values already in the lab and a little bit in the lecture. And we're going to be comparing that to our alpha level, alpha value, sorry. So where we have a circumstance where our p-value is less than our alpha value, we're going to decide to reject the null hypothesis. On the other hand, if our p-value is greater than our alpha value, we're going to fail to reject the null hypothesis. So this is how we can use our p-value to compare it to the alpha value to determine whether we're going to reject or not reject the null hypothesis. So you can think of these two errors, right, in this type 1 alpha and type 2 beta errors within this kind of grid right here, where we have the truth up here. So this is actually what happens in reality, positive or negative, right? So that's actually reality, whether something's positive or negative. And this is the result from our test, positive or negative. So when our test, right, gives us a positive result, where in truth there is a positive result, everything's great, right? We have a true positive result from our test. If our test gives us a negative result and the truth is also a negative, right? Everything is also good again. We have a true negative result. It's only when we have the different results from our tests, so we get a positive result from our test, when in reality we have a negative in truth. That's when we're going to have that alpha value creep in there, right? We're going to be committing that type 1 error. Alternatively, right, same kind of idea. If our test tells us, it gives us a negative result, when actually in reality we have a positive result, we're going to have the opposite error. We're going to have a false negative. So you can also think about type 1 and type 2 errors in terms of a legal context, right? So you've probably heard of the threshold, guilty beyond a reasonable doubt in criminal systems. The threshold to convict somebody is very, very high. You can think of that threshold beyond a reasonable doubt as basically being the alpha level. So imagine somebody standing trial for murder, right? In this case, the type 1 false positive would be that the innocent person is being sent to prison. So we have an innocent person, right? So the presumption of innocence is kind of like our null hypothesis. And if that person actually is innocent and the trial finds them guilty and sends them to prison, well, the outcome is essentially a type 1 or false positive error. Alternatively, right, imagine that person is guilty of murder, but the court finds them not guilty. So in this case, a false negative type 2 error would be seeing a guilty person being set free. So if we look at that in terms of our grid here again, imagine, right, the truth is the person being guilty or innocent. And then the result from the trial, the verdict, is guilty and innocent. So the person actually is guilty in reality, and the trial finds him guilty, right? Everything's perfect. The trial worked. But if that person actually is innocent, and the verdict from the trial finds him guilty, right? That's where we're going to have a false positive, right? So we're sending, in this case, an innocent person to prison. The default or the null hypothesis is that, right? The presumption of innocence. So if we have an innocent person that is found guilty in the trial, that is an example of a false positive. Alternatively, right, if we actually have the person that is guilty and the verdict of the trial finds him innocent, then we're going to have a false negative. In that case, we're going to have a guilty person, right? In reality, it's guilty, but the trial is going to set them free. And then if we have an innocent person, right, in reality, that is found innocent by the trial, right, everything's good. No error is being committed. So again, we can think about the error hypothesis in terms of stat tests, kind of like with these the trade-off between type 1 and type 2 errors, right? As we start to decrease the probability of committing a type 1 or false positive error, we increase actually the probability of committing a type 2 or false negative error, right? So there's always a trade-off. As we protect against committing a false positive, we increase our chances of committing the other type of error, a type 2 or false negative error. So sometimes the idea of how good a test is referred to as the power of a test. And the power of a test, or how good or effective a test is its ability to reject a false null hypothesis. So the truth out there is that you should reject a null hypothesis, and the test actually gives you the result to reject that null hypothesis correctly. So the better the statistical test is able at rejecting false null hypothesis, what's called the power of your test is increased. So the way that we can calculate the power of a test is basically taking, right, probability of 1 and subtracting the beta, which is a type 2 probability from that. So just a video there showing more of the idea of the errors and power of statistical tests. Another video right there if you want to look at that. Okay, let's get into, right, just for review, here's our 6 steps that we're going to take in doing our classical hypothesis testing, starting with stating the null alternative hypothesis, right, all the way up to actually calculating the test stat, and then from that determining whether we're going to fail to reject or reject our null hypothesis. So the best way to learn this and exactly all this what I'm talking about is actually do some examples. So let's do a scenario here. So imagine you take a sample of 250 households in the village of Marengo. I picked this village of Marengo. This is where I grew up in Saskatchewan. And from this sample of 250 households, you found the average size household has 2.68 people, right? That's the mean number of people in each household. Now you want to compare this to the average national size of a household, which is 2.61. So there's a difference, right, between the sample mean and the overall population mean, in this case being Canada, the national average. But you're wondering whether this difference is trivial or whether it's significant. So again, we're going to be using the, so just to go over what our data is here. So our standard deviation is 2.07. So the first thing that we're going to do with our classical hypothesis test is determine the null hypothesis and the alternative hypotheses. So the null hypothesis is that there's no significant differences in the average household size between Marengo and the national average. The difference that we see is just due to random sampling error. Alternative hypothesis is that there is a significant difference between the average household size between Marengo and the overall national average. So think about this right here. What in this case would be the type 1 error, and what would be our type 2 errors? So in this scenario, we're not really caring about what direction our test is going to be in. We're only wondering if there's a difference between Marengo and the national average. We don't care whether Marengo is greater or less than the national average, only that there's a significant difference. So in this case, we would perform a non-directional, aka a two-tailed statistical test. So you might be wondering, what are some of the cues that you can use to determine what type of stat test you want to use? Well, first thing is what's being tested, what's your research question, and what's your sample size. That's going to determine whether you're going to use a Z-stat versus a T-stat. So in our scenario, because we're comparing the mean from a sample to the overall population mean, we're going to use a one sample difference of means test. In this case, since we have a relatively large sample size, right, it's greater than 50, we can calculate the Z-stat, sometimes called the Z-score, to determine the test stat, and from that, the p-value as well. Right, so what we have here, right, the test stat that we're going to use is going to determine mostly by our sample size. So if we have an n greater than 30, the test stat that we're going to go with is the Z-stat, right, our stat with the normal distribution. If we have a sample size which is 30 or lower, we're going to calculate the t-stat. Now you can see that the t-stat and the Z-stat are very similar, but the t-stat accommodates or adjusts for the small sample size by this small change here, where we have n, instead of just having n, we have n minus 1. So similar ways in which the Z-stat and the t-stat are calculated. So once we're done that, we're going to select our level of significance. Remember again that the level of significance is going to determine, right, the probability that we're going to commit a type 1 error. So, right, also called the alpha level, right, alpha value. So usually the common significance levels are 0.01, 0.05, 0.1. So for this example, we're going to use an alpha value of 0.05. But what does that 0.05 actually mean, and why do we use the 0.05? Well, it's a little arbitrary, but 0.05 is commonly used because it gives us about a 19 out of 20 probability that we're not going to commit a type 1 error. So for our test, we have an alpha level or value of 0.05, but because we're performing a two-tailed test, we're going to split that 0.05 rejection area in half. We take that 0.05, divide it in half, which gives us 0.025. And so if we look at our areas of rejection and non-rejection, right, we have 95% of the area in the non-rejection zone, and then we have the other 5% of the area split between the left tail and the right tail of our distribution. Anything in here is going to be our non-reject zone. Anything that falls where our test stat falls within these hashed areas is going to be where we reject the null hypothesis. So you can see that for this case, we have a z-score between minus 1.96 and plus 1.96. We're going to fail to reject. If our z-score is greater than 1.96 or less than minus 1.96, we're going to reject the null hypothesis. So basically, right, two scenarios. If we were going with the one-tailed test, right, we would put all of the rejection zone in either the left tail or the right tail, which would correspond to a z value of minus 1.65 or plus 1.65. Since we're doing a two-tailed test, we're going to split that rejection zone, right, between the left tail and the right tail, and that gives us these z values that are much further out, in this case being minus 1.96 and plus 1.96. So we've selected our level of significance, our alpha value. Now we're going to delineate the regions of rejection and non-rejection, which I basically showed you in the last couple of slides there. So for our 95% confidence level, right, our alpha level is going to be the complement of that. So 95% confidence level gives us an alpha level of 0.05. Since we're doing a two-tailed test, we're going to take that 0.05 and split it into two. Right, so you can think about it as this in terms of delineating your areas of non-rejection and rejection, right? So anything that falls between minus 1.96 and plus 1.96, we're going to fail to reject. Anything more extreme than those two critical values, right? In this case, these are referred to as our critical values. We're going to decide to reject the null hypothesis. So once we get those areas delineated, we're actually going to go ahead now and calculate the test stat. So here's our data from our scenario, right? There's our sample. Here's the population mean that we're comparing it to. Our S, our sample standard deviation, and 250 for our sample size N. And since we have a sufficiently large sample size, we're going to be calculating the z-stat, which is basically taking our raw data value, our sample average, in this case, a sample mean, minus the population mean, divided by the population standard deviation if we have it. If we don't have it, we can replace that by the standard error. So if we do the actual calculation, you should get a z-score of 0.53. Okay, but what does that mean? What does that tell us? Does that tell us to reject the null hypothesis or not? So that's going to bring us to our last step, using our test stat to make a decision whether to reject or non-reject. So how do we know to reject? Right? If the test stat is closer to the middle, or 0, than the critical value, and the p-value is greater than our set alpha value, if that's our scenario, we're going to fail to reject, aka we're going to retain the null hypothesis. Alternatively, if our test stat is more extreme or further away from 0 than the critical value, and our p-value is less than our set alpha level, in that case, we're going to decide to reject the null hypothesis. So again, we calculate a z-stat of 0.53, right? That z-stat of 0.53 falls between our critical values, those two critical values right there. In other words, our z is closer to 0 than the critical values. So that would tell us that we're going to fail to reject the null hypothesis. And it really would not even have to calculate the p-value to determine that we're going to fail to reject the null hypothesis. So if we look at this in graphic form, right? Here's our critical values, right? Minus 1.96, 1.96, and our calculated z values, right? It falls, right, closer to 0, which is mu right in the middle here, right? So because our z value is less extreme than our critical values, right, we're going to fail to reject the null hypothesis, that there's a difference, a significant difference between the sample size and the population. Like I said, we do not even have to calculate the p-value, but let's look at it and calculate it anyways. So the one-sided p-value for a z of 0.53, right? I'll show you this on the other side, is equal to about 30%, 0.3. Since we're doing a two-tailed test, we're going to take that one-sided probability rejection area and multiply it by 2, so we get 0.59 close to 0.6. Right, so if I go and, right, that's how I determine where I get that 0.7019. I'm going to subtract that from a total probability of 1 to get 0.298. Right, so basically that the z-score of 0.53. To the right of that, we have a probability of 0.298. To the left of that, we have a probability of 0.7019. Both of those, of course, add up to a total probability of 1. Right, so both by looking at the z-score comparing to the critical value and our p-value, we determined that we're going to not reject the null hypothesis, and therefore our conclusion is going to be that even though we do see slight differences between the average household size between Marengo, it is not statistically significant, right? Be different from the national mean average household size. So we can also look at the p-value and compare that to our alpha level or alpha value to determine whether we're going to reject or non-reject. So for our case, right, here's our critical values. Here's our calculated Z scores. So if we look at the alpha value, right, we split it between both the left side and the right side, taking that 0.05 and split it into half. So this would be our area of rejection on both sides. But those p-values, right, for minus 0.53 and plus 0.53 corresponds to p-values of 0.2981, about 0.3. So if we add those two values up, we get a total p-value of about close to 0.6, right? So a much higher p-value compared to our alpha value. So another reason why we would fail to reject. So we would need a p-value which is less than our alpha value for us to reject the null hypothesis. But we can see in this case, the p-value is much, much greater than the alpha value. Okay, let's do another one sample means test. In this case, our background, say, scenario is to combat obesity. Australia in 2009 reduced the size of their chocolate Mars bar to 53 grams. But say, for instance, the quality assurance person at the Mars bar factory wants to make sure their weights are equal to or less than 53 grams. So to do this, there's a known standard deviation of the population, right, of 6.7 grams. And to determine whether these Mars bars are being produced either equal to or less than 53 grams, she takes a sample of 35 bars. And from that 35 bars, she gets a mean weight of 54.9 grams. So let's set this up in a classical hypothesis testing. So the first thing we're going to want to do is formulate our null and alternative hypothesis. So in this case, for our Mars bar, we're wondering, right, whether our Mars bars, right, is less than or equal to 53 grams, or whether it's greater than 53 grams. So if the null hypothesis is that it's either less than or equal to, and if we reject that, we know, or our test tells us that our Mars bars are heavier than 53 grams. So the second step, right, what test are we going to use? So we have a sample size of 35 bars, a population standard deviation of 6.7 grams. So again, we're comparing a sample to see if it came from a larger population. So the test that we're going to be running is a one sample means difference test, just like in the previous example. And because we have a sample size, 35 bars in our sample, it's greater than 30, and 30 is kind of the threshold that we're going to use. We're going to use the Z test, or calculate the Z statistic. So what step 3, what's our level of significance, aka our alpha level, right? So if we're going to be 95% confident, we're going to select an alpha value of 0.05. If we want to be even more confident, 99%, we're going to select an alpha value of 0.01. But let's say in this case, we want to have a alpha level of 0.05. So we want to be 95% confident that we're going to get the right answer. Step 4, we're going to determine what our regions of rejection and non-rejection of the null hypothesis are, right? So in this case, since we're testing to see whether the Mars bars are heavier than 53 grams, this is going to be a one-sided or directional test. So we're going to put all of that 0.05 rejection area in the right tail. So essentially what that's going to look like is this. So there in the green is our non-rejection zone. There's our mean, right? And we're going for population of 53 grams. And if we find that our sample is outside of that, we're going to land, and if we land in the rejection zone, we're going to reject the null hypothesis. So again, we have a large enough sample size so we can calculate the Z-stat. So again, our Z-stat, we're taking the sample mean minus the population mean divided by the standard deviation. In this case, we know the standard deviation of the population, so we don't have to estimate it by the standard error. So there's our formula again. So in our case, right, our sample is 54.9 grams minus the population mean divided by the standard deviation of the population. That gives us a Z-score or Z value of 1.68. But now we have to figure out, what are we going to compare that Z-score to? What's going to be our critical value? So here's just an Excel, right? I've set up the problem here. There's our population mean of 53, sample mean 54.9, sample size 35, and there I've calculated, right, my Z-score using those values. All right, so we are dealing with a 95% confidence level. We're doing a one-tail test. So for our one-tail test, our critical value that we're going to compare our Z-stat to is going to be 1.65. Again, our critical value divides our rejection zone from our non-rejection zone. Right, so that's what I calculated. Right, there's my Z-stat that I've calculated. That's what I'm going to be comparing. So there's my critical value, 1.65 for an alpha level of 0.05. My Z-score is 1.68, which lands me just within the rejection zone. It's close, and this is why it's important to select an appropriate alpha level beforehand. But you can see here my Z-score is a little further away from the mean compared to my critical value, so that lands me in the rejection zone. So in this case, because I land in a rejection zone, I'm going to, based on this, decide to reject the null hypothesis. that leads me to my conclusion. Right, so we can again determine this in two ways. We compare, like we just did, the z-stat to the critical value, but we can also compare the p-value to our established alpha level. So because we had a z value of 1.68, and that's more extreme than our critical value of 1.65, based on that, we're going to determine that we're going to reject the null hypothesis. And from that, we're going to conclude, right, that our Mars bars are actually heavier than they should be based on that sample. What about the p-value? So again, we're doing a directional test, so we're going to look up the right-tailed probability for a z-score of 1.68. So we go back to our z table here, right? 1.68 right there corresponds to probability of cumulative probability of 0.9535. So if we look at this table here, right, there's my rejection zone, which is established by my alpha value, which is 0.05. So this is 5% of the area underneath the red area right there. My p-value, right, the 1 minus that 0.9535, because my probability is in the right tail, right, is 0.0465, which is slightly smaller than my established alpha value. So another reason why, again, because my p-value is less than my alpha value, again, I'm going to decide to reject my null hypothesis. So basically, again, what the p-value tells us, in this case, with a p-value of 0.0465, that there is about a 4.65% chance that that sample actually belongs to that overall large population. So it's a relatively small chance that that sample actually belongs to the same group that that population is from. So there's less than a 5% probability that will falsely reject the null hypothesis based on this. We have about a 4.65% chance that our statistical test is going to tell us to falsely reject the null hypothesis. In other words, commit a type 1 error. So imagine instead of doing a one-tail or directional test, we instead change to do a two-tailed test. So instead of caring whether we have a heavier weight or not, we maybe just are curious on whether our sample is significantly different from the expected value. So we can change, in this case, from a one-directional test to a two-tailed non-directional test. Let's see how that's going to change. First of all, our null hypothesis is going to be, in this case, right, our population mean is 53 grams. Our alternative is that it's not 53 grams. It doesn't matter which direction, whether it's higher or lower. It's only whether there's a significant difference or not. So let's compare, right? So again, let's stick with the confidence level 0.95. So in our first example, we're using a one-tailed test where we had a critical value of 1.65. We had the alpha, right, 0.05 area all in the right tail. So if we switch this to a two-tailed test, right, now we're going to split that alpha area into two and put half of it on the left side. And our critical value is going to change from 1.65 for the one-tailed test to plus 1.96 and minus 1.96 for the two-tailed test. So that's for the 95%, but the same kind of idea, say if we were doing for a 99% confidence level. In that case, we have more extreme. If we're doing a two-tailed test, there would be our critical values there, and we'd split the rejection zone in the two tails. But if we change that from a two-tailed test to a one-tailed test, right, we would put all of the rejection area just in the one tail. So that's the kind of the idea between the difference between a one-tailed and a two-tailed test. So going back to our example, right, one-tailed versus two-tailed tests. For the previous one-tailed test, we calculated a z-stat of 1.68. So we can keep that same z-stat because our scenario didn't change, but now what's going to change is that we're going to have a different critical value to compare that z-stat to. And we're both going to have a positive and a negative value to compare to. Right, so there's our z-stat that we're going to that we calculated for our example, minus 1.68 plus 1.68. We have both a positive and a negative value now because we have a two-tailed test. In our one-tailed test, we compared that to a critical value of 1.65, which because the z-stat landed outside of it, we rejected a null hypothesis. But now, since we're doing a two-tailed test, we see that our critical values are further away from the middle compared to our z-stats. So we actually get the opposite result by doing a two-tailed test compared to a one-tailed test. Same idea with the probability, or p-values. So imagine if you wanted to do this again and you wanted to be even more sure, instead of having a 99% confidence level, and you want to go to a 99% confidence level that the bars from your sample are not significantly heavier than the expected 53 grams. So what steps would you follow in performing the test, and what does by doing the steps of the test, what do you actually end up telling your boss? So you can do this calculation yourself. It's in the class calculation number 4 tab in the Excel spreadsheet. Right? So we're going to be using a confidence level of 99%. So there's the difference between the one-tailed and a two-tailed test right there. So if we do the calculation, you get a z-stat of 3.01. Our critical value is 2.33. So since z is further away from 0 or mu, again, we're going to reject the null hypothesis. We'll go and look at the p-value. Right, we subtract the cumulative probability value, 0.9987 from 1, gives us an extremely small p-value. Again, the p-value tells us the probability that that sample actually belongs to the same group as that overall population. So we can see by that very, very small p-value that there's a very remote chance that they're from the same group, and that instead that the sample is different from what is expected. So since we have a very small p-value, which is less than our set alpha level of 0.01, again, that tells us to reject the null hypothesis. So I'll end off right there. Again, here's some good videos from Khan Academy. If I didn't explain everything perfectly, a little bit about hypothesis testing and p-values, two-tailed versus one-tailed tests, and z-stats, calculating z-stats versus t-stats. So I'll end the video off there today, and there'll be one more video in this week's lecture series.